So, last class we have discussed how to solve the LP problems using two phase simplex method. We have taken this example, maximize this function subject to this constant, and y 1 is greater than equal to 0 means non negative number, and y 2 is unrestricted sign. So, this y 2 we have to convert into a, by introducing two new variables. We have defined y 2 is y 3 and y 4, which is individually that y 3 y 4 is greater than equal to 0. But this problem we have to convert into a standard LP problems, that we have seen how to convert the standard LP problems. After converting this one, then you see this type of equation, when you will get this type of inequalities greater than equal to equalities, then we have to introduce a variable which is called artificial variable. This artificial variable is that x 6 in our case, and that artificial variable we consider, we have to minimize. That means, we have considered the artificial variable x 6 as a w 6 w, and this simultaneously you have to optimize that, minimize two function, objective function. One is x 6, which is we denoted by w 6, another is our original objective function. And this first phase, what we optimize, that x 6 is a w, this we have minimize this one in first phase of the tabular form. After the first phase, we got the solution. After completing the first phase, we got the solution of this, that is our artificial objective cost function value is omega is equal to 0. That should come omega is equal to 0 or x 6 is equal to 0, and corresponding the design variables, what we consider x 1, x 2, x 3, x 4, x 5 and x 6 is this value, we got it. Okay. Then next that phase 2, since w x of 6 is optimized, minimized, then we ignored the what is called calculation in the table x 6 variables. So, you just ignore x 6. So, in second phase, it will just find out the cost function of the original systems, original objective functions, it will find out. And during, after completing the second phase, we got the function value is f is equal to 12, and corresponding the variables value x 1, x 2, x 3, x 4, x 5, we got it, these values x this. So, if you look carefully this one, we have, this is our basic functions of that one. If you plotted that one, we have seen that this basic function, if you plot it graphically, if you see, this is the our equation, one of the constant is this one. When we put y 1 is equal to 0, x 2 y 2 is equal to 6. So, this is our 6. When y 2 is 0, y 1 is 4, that is our 4 0 coordinate. This is 0 6 coordinate. Agree? Then another constant is 2 y 1 plus 3 y 2 is greater than equal to 6. Our original problem, if you see, putting would just to draw this equation straight line, y 1 is 0, y 2 we will get it 2. So, this value is 2. Then y 2 value is 0, then where it cuts the x axis, this one, that is equal to our 3. So, this coordinate 3 0, this coordinate is 0 2. Okay. So, it cuts the x axis, if you see this cuts the x axis, y axis, this is called, let us call point B, this is point A, and this is this intersection of two straight line is C. Now, according to our problem, if you see y 1 is greater than equal to 0, that means y 1 indicates the right half of this vertical line y 1, the whole vertical right half of the vertical line, and y 2 is unsigned. That means, y 2 value can be positive and negative. That means, that may be above this line, above this horizontal line, or below this horizontal line. So, if you see carefully this one, our feasible region is that portion only of our corresponding problems. and in this case our objective function, if you see our objective function is nothing but a z, maximize z is equal to y 1 plus twice y 2, and that is we have to maximize. And graphically you see when this function value will be 0, this is the equation of the system, this function value is 0 when this passing through this origin this. So, this is the equation of that line. So, that means we are finding out the what value of y 1 y 2 in the feasible region, the function value will be maximum. This is the maximum we want, maximum value of this function. So, if you just move this line parallel to this that line which is passing through the origin, you will see maximum value of this function value will get at this point B point, parallel to this one, parallel to this objective which is passing through this one. So, that one will give you this one. Let us see in first phase of our problem what we got it. If you see, recollect that first phase, in first phase, first iteration we got the value of, if you see, x 1 0, x 2 0, x 3 0, x 5 0, and from this one what we can say, y 1 is nothing but x 1, that means y 1 is 0, y 2 is what we have defined, y 2 is nothing but a x 2 minus x 3. So, x 2 minus x 3 both are zeros. So, this point origin point is the in phase 1 first iteration we got it this point y, but this point is not in the infeasible, and next iteration what we get it in the first phase, next iteration if you see, we got x 1 is 0, x 2 is 2 and x 3 is 0. In other terms, because y 1 is equal to our x 1, that means our y 1 value is 0, if you see y 1 value is 0 and then y 2 value is x 2 minus x 3 means 2, that means we got this point. So, and immediately we can say the function value is increased from previous value. Previous what at this point function value was 0, at this point one can find out what is the value of this, it will be increased. Physically also you can say this straight line is moving parallel to the and cuts y axis some value of this, instead of 0 it is cutting this one. So, this and this is the first phase after completion of first phase. Now, see after completion of second phase, which will minimize the function of that one. In other words, our original function will be maximized, because we have converted into standard LP problem, that is why minimization term we are using. So, in the after the completion of second phase of this one, our x 1 value is, you see, x 1 value is 0, x 2 value is our 6. So, this indicates x 1 0 means x 1 in y 1 is equal to x 1, that means y 1 is 0, y 2 is what, x 2 minus x 3, the way we have defined. So, 6 minus 0, 6. So, this is this point. On this point is I will give the maximum value of the function of this time, agree. So, graphically also one can represent this one. So, today we will discuss what is called, we can solve the what is called LP problem by using primal and what is called dual problems, considering the standard primal and dual problems. So, primal and dual problem. So, what is primal problem? First, standard primal problem is what we will define, standard primal problem. So, first we convert this problem into a standard primal problems. So, what is this? What is a standard primal problem? Maximize ZP is the objective function is that way. We have defined x 1, d 1 x 1, d 2 x 2 plus d n x n. We have a n variables are there. you can write into vector form this d transpose x, x is a dimension n cross 1, and d is a vector, column vector is your d 1, d 2 dot dot d n, and this dimension is n cross 1. So, this is subject to a 1 1 x 1, a 1 2 x 2 plus dot dot a 1 n x n is less than equal to E 1. Similarly, second equation, constant equation, and constant is of this type, less than equal to x 2 1 x 1 a 2 2 x 2 plus dot dot a 2 n x n less than equal to E 2, and so on. In this way, we have a n inequality constant less than equal to type. So, it is a m 1 x 1 plus m 2 x 2 plus dot dot a m n x n dot dot is less than equal to E m. So, and also x j is greater than equal to 0 for j is equal to 1 2 dot dot n, and E j E I is equal to 1 2 dot dot I, we have a m constants are there dot dot m. This E I is unrestricted in sign, it can be positive, negative, 0, whatever may be, it is unrestricted in sign. So, no restriction, you can just write it, no restriction on its sign. Okay. So, this is called standard primal problems. So, this you have to, if you are given the LP problem, if you want to convert into a standard primal problem, you have to convert into this structure. Mind it, from the standard LP problem, difference is there, the right hand side of this one is not, it's not restricted, it can be unrestricted, it can be any sign, positive, negative, all these things. So, a set of equation I can always write in terms of matrix x a into x less than equal to E, that E dimension n cross m cross, there is m cross 1, this dimension is n cross 1, immediately I can write it, this dimension is m cross n, and E is a vector. Components of E are E 1, E 2, E 3 dot dot E m. This. Suppose in this equation, if you get, you are given a LP problem which having a equal to sign, and we have discussed earlier, if you get that equality sign, say like this way, equality constants, if you get it, let us call something like 2 x 1 plus 3 x 2 is equal to 5. That equivalently, because I have to convert into, if you want to convert in the standard primal problem, you have to convert into less than equal to. Okay. So, this can, I can do it immediately, I can write by set of two equations, 3 2x plus x 2 is less than equal to 5, another I can write 2x plus 3 x 2 greater than equal to 5. Equivalently, I can write it. These two equivalency is same as that one. Or if you have a equality of this type, let us call inequality, if you have a inequality constraint of this type, then how to convert into a standard primary problems, this one. So, suppose you have a equality is like this way, 10 x 1 minus 6 x 2 plus 7 x 3 is greater than equal to 12. So, what we will do it, both side you multiplied by minus. So, if you multiply by both side minus, that it will be 10 x 1 plus 6 x 2 minus 7 x 3 is less than equal to minus 12. So, this has converted into a standard primal inequality form. So, this keeping this thing in mind, any LP problem I can convert into a standard what is called primal problems. Now, what is the dual part of this one, that means standard dual problems. This problem, this standard primal problem also referred as normal maximization problem. This standard LP problem also referred as normal maximization problem. Now, next is what is the dual problem of this one. Next is the dual of this problem. Dual of primal problems. What is the dual of primal problem? This what is written maximization? I will write minimizations. Agree? Minimize. That let us call I have denoted by FD. That I have denoted by ZP. P stands for primal problems, means original problem, and dual stands F of D is this is a minimization. Then how will you write it? See, dual problems. Whatever the inequality constant you have a m inequality constant, and right hand side of the inequality constant E1, E2, em. That quantity will come to the objective function of the dual problems. Agree? So, you will write it this E1 multiplied by some dual new variable Y1, dual variables you can say, E2 multiplied by Y2, the new variables in this way. So, if you have a m equations are there, m inequality equation there in standard primal problems, the dual problems you will have a new m variables. Instead of x variables in pi by x n variables in the primal problems, in dual problems you will get m variables, new variables you have to introduce there. So, I am writing this one E1 into Y1, E2 into Y2, agree, E2 into Y2, and this E1, E2 is known to us, and then in this way EM, YM. So, in that standard primal problem inequality constant we have m inequality constant, in dual problem we have to make new m variables y1, y2, y3, and objective function which is the minimization of FD is formed with the coefficient you have got in the right hand side of the primal problem, agree, that coefficient, that values you have to introduce in the objective functions. So, this is minimized subject to. So, this I can write, if you write in a vector form, E transpose y, and y is what, m cross 1, and where is E is here? E is a vector of dimension m cross 1, agree. Our problem is now minimize this one subject to, say this one, this that A1 column wise I am reading, A1 multiplied by Y1, A21 multiplied by Y2, Mn similarly Mn multiplied by Ym. So, I am writing first constant equation A11 multiplied by Y1, A21 multiplied by Y2, and dot dot A M1 multiplied by Ym, and whatever the coefficient was there in the standard primal problem in the objective function coefficient, that coefficient will come in the right hand side of the inequality constant in the dual problem. So, our inequality constant of this type greater than equal to, and this is the first constant corresponding to the first one, it will come D1. Similarly, see, take the second column multiplied by second column is A12 multiplied by Y1, A22 multiplied by Y2. In this way, we have AM2 multiplied by YM is will be greater than equal to second coefficient associated in the standard primal problem, agree, in the objective functions. So, this equal to, I can write it next, A12 Y1 A22 Y2 plus dot dot AM2 YM is greater than equal to D2. And if you continue like this way, last one will be A1M Y1 plus A2M 2M, agree, A2M, here is 2M, A1, sorry, last will be A2M, see A1 2 2 1 M2 1, this is M2 YM, agree. So, last one will be M, this will be M row, M1, last row you see, what will be the rush, this I have written this A1N, sorry, A1N, I am writing this one, last one. There how many equations will be there? There will be n equations. So, last column is A1N into Y1 plus A2N, see this one 2N, the Y2 plus dot dot A MN, agree, into YM, that equal to DN. So, you see that how many coefficients in standard primal problems are there in objective function? There are n coefficients are there, and that n coefficient will come in the dual problem inequality constant. That means, n inequality constants will be coming here. So, we have written these things, if you say A1 A11 Y1, then A12 this agree, then this A1M YM, and similarly this is the second equation, we will get it which is D2, and the nth equation it will be Dn. So, this is we will get a set of inequality and inequality constraint with the help of standard primal problems objective function coefficient will come to the right hand side of these inequality constants. And if you see this inequality constant, this if you express matrix form, it is A transpose of Y is greater than equal to D. D is your dimension n cross 1, agree, and this M is M cross 1. So, this we can write, and here Y I is greater than equal to 0, agree, and D1 D I varies from 1 to dot dot n. This has no restriction on its sign. So, now in short, what is standard primal problem? Structure is like this way: maximize ZP, D1, D2, D3 are the coefficient associated in the objective function, and x1, x2 dot xn is the design variables, and that you convert into a this type of inequality form, agree, and this E1, E2, En are there is no restriction on its sign, but these design variables are all greater than equal to 0. In turn, I can write matrix vector form into this form. This how will you convert into dual problem of this is a dual problem of that primal problems, that whatever the coefficients are associated in objective function of standard primal problem, that will come right hand side of the inequality constraint of inequality constants of dual problems. So, it is coming right hand side d1, d2, dt, and what is the expression we will write it inequality constant? This column, consider this column a11 into y1, a21 into y2 plus a dot dot plus am1 into ym will be greater than equal to d1. Similarly, second column, third column in this thing. So, since we have a in primal problem n coefficients are there, we will get n constants are there. And whatever the right hand side in the standard problems, how many equation inequality equation there are m equations are there. So, that variables will go in the dual problem objective functions, it is going, and corresponding m new variables are introduced. So, this is called the dual problem of the primal problems. Agree? And observation, if you see this observation of that one, it is clearly say that number of dual variables, that dual variables is y1, y2, y3 dot dot ym is same as the number of primal constants. How many constants are there? M constant, and dual variables are let us say 1 y1, y2, y2. So, number of dual variables is same as number of constants in the primal problems. This is the first observation. Second observation, number of dual constants is same as number of variables in the objective function, primal variables. Number of constants in the dual problem is same as number of primal variables in the primal problems. This is the second observation we got it. And coefficient associated with the standard primal problem, coefficient associated with x is a matrix. What you get coefficient matrix in the dual problem, primal problem. If you take that transpose, that will get you the coefficient matrix of dual problems. This is the third observation we have seen. Then we can see this one, that inequality constants are reverse in direction. The primal problem inequality is less than equal to type, and dual problem is reverse in direction greater than equal to. This is the fourth one we will get it. And minimization or maximization problem of primal problem becomes a minimization problem of dual problems. So, you see this is the maximization problems now become a minimization problem of dual problems this. So, these are the observation we got it this one. And you have seen this coefficient associated with the primal in the objective function, coefficient associated with the variables that comes in the what is called objective, that comes in the dual problem inequality constant right hand side, and vice versa, which is coming in the standard problem inequality constants the right hand side, what is coming E1, E2, E dot dot EM, that will come as a coefficient in the dual problem objective functions. And this primal and the dual variables are non-negative. That means xi is greater than equal to 0 and yi is greater than equal to 0. This. So, keeping this thing in mind, we further see how to convert that a dual problem into primal problems and primal problem into dual problem. We can do it. So, let us take in one example and we will see how to solve it. So, let us call the example. The primal and dual problems using simplex method. So, let us I will give you the primal problem, convert into dual problem. Agree? So, primal problem, primal problem. So, what is the primal problem? Maximize ZP is given 5 x 1 minus 2 x 2, which I can write it D transpose general structure into the X. This is our 2 cross 1. If you see our D, where D is equal to 5 minus 2, which dimension is 2 cross 1, subject to 2 x 1 plus x 2 is less than equal to 9, x 1 minus 2 x 2 is less than equal to 2, minus 3 x 1 plus 2 x 2 is less than equal to 3. Agree? And x I is greater than equal to 0 for I is equal to 1 to this. Now, you see it is already in standard what is called primal problem. If it is not there in standard primal problem, you convert into standard primal problems. Okay? So, this is the standard primal problems. First, your job is, let us call I given the problem, you convert into a standard dual problems. And now, you see, so this if I asked you, so let us call first I asked you, this is the primal problem, solve this problem by using simplex method. Then you can solve it, because you have to convert this thing into a standard LP problems. This is one way. And if I tell you that this is a primal problem, convert it dual problem and then solve it by using simplex method. That is why. Why you have to convert into a dual problem? Sometimes when you convert from what is called dual, you have a standard problem to dual problem, the computational advantage you can get it while you are solving the multi-objective optimization problems, linear optimization problems. That is maybe the one of the advantage you can get it from this one. So, let us see first our question is convert this thing into standard LP problem and then solve it, standard LP problem then solve it. But I will not solve this by standard LP problem, because I have already discussed how to solve a standard LP problem using simplex method, means in tabular form, or it is a algebraic approach or matrix form, you can solve it. So, solution. Suppose you are asked to solve the problem is primal and dual problem using simplex method. So, this solution, convert standard LP problem and then solve using simplex method. So, I will just tell you how to convert the standard LPM. What is the standard LPM? This you have to convert equal to sign, and not only that, and right hand side of this equation must be positive. Right hand side of this equation must be positive. Right hand side of this equation must be positive. This is already in positive sign. So, we have to introduce in this equation one slack variable, here one slack variable, here one slack variable. Suppose you have a this is the primal problems you have. Suppose in the so then after that you can solve it. So, let us call how to convert this thing into a standard, what is called I just convert into a standard LP problem. So, our standard LP problem minimize, that is ZP f of x is equal to minus ZP, which is equal to, see this one, minus means minus 5x minus, it is minus there. So, it will be plus 2x, and this you can convert by adding one slack variables, because this is less than this, you have to add some slack variable, and slack variable value greater than equal to 0. So, that slack variable I introduce as a x 3. So, 2 x 1 plus x 2 plus x 3 is equal to 9. This is the slack variable. Then we can find out that next equation, you see, similarly second and third I can write it. So, second equation is x 1 minus 2 x 2 plus x 4. So, this is also slack variables is equal to u 2. Then third equation, you see, minus 3 x 1 plus 2 x 2, and I have to add another slack variables with this one, so that it will be equal to 3. So, this is also slack variables. And right hand side of this equation all are positive. So, our x I is greater than equal to 0, I is vary to 1, 2 dot dot 5. So, this is converted into a standard LP problem. Then you know in tabular form how to solve this problem, agree, by simplex method, that you solve it. If you solve this problem, then you will get the solution of this one, that our x 1 optimal value of this one, you will get 4, x 2 star you will get 1, x 3 is equal to x 4, this star it will get it 0, then x 5 star you will get it 13. So, this is the solution, and in if you complete this solution in tabular form, that our basic variables are x 1, x 2 and our x 5. These are the three, this and this is the basic variables, and remainings are non-basic variables. This is non-basic variables. So, immediately what is our minimum value of the function? If you just put it here, that x 1 is 4, means minus 20, minus 20 plus 2, f d or f is, you will get it, f star is minus 18. Our problem is, if you see our original problem is maximization problems, agree, our maximization of problem of that one. So, that will be a, our maximum z will be, if you say, plus 18, agree. So, this is the solution. You have a given LP problem. If you are asked to convert into a dual, what is called primal problem, and then solve it by using simplex method, you have to do like this way. Now, next is, I told you, I mentioned you, if you convert the primal problem, that is why I called it, if you convert the primal problem into dual problem, that maximization problem you convert into what is called minimization problems, and the way it is converting into dual problem, just now I explained it. If you convert it into dual problem and then solve it by what is called simplex method, agree, but that variable dual problem variables are new things, that is no way linked with the, I mean no way direct relation with the our primal variables x 1 x 2. So, there must be some link between the dual variables and our primal variables, because our objective is to find out the primal variables of that one. There are two objectives in mind. If you convert the primal problem into dual problem, we can get the what is called the computational advantage while we will solve the multi-objective optimization problems. Agree? And when you are going in that domain, what is called dual problem solution, our variables are y1, y2, y3 dot dot ym. That variables we have to make a direct connections with the x. How to convert that values of that dual variables values, how to convert into a that standard variables values, that is next issue. So, let us now we convert our problem is standard LP problem. If you see this standard LP problems, this standard LP problem, now we will convert into a dual problems. How will you do? Now, you remember first you have to minimize that function. How will you objective function of that dual problem you will be considered? Whatever the coefficients are there, that coefficient will come in the objective function of dual problems, and that dual problem will be minimization of the objective function. So, if you do this one dual problem now, keeping that in mind, minimize f of d is say 9 to x. There are three variables, three what is called in standard problem, three inequality constants are there. 9 into y1, 9 into y1 new variables, then it is a 2 into y2, that 2 is y2, then 3 into y3. So, this is our objective function. Dual problem objective function is subject to. Now, see this one, 2 into y1, this coefficient is 1, plus y2, then minus 3 into y3. So, I will write it this first equation, I will write it 2 y1 plus y2 minus 3 y3 is greater than equal to your 5. So, 2 y1 plus y2 minus 3 y3 is greater than equal to 5. That all coefficient of standard LP problem or standard primal problems will come right hand side of the inequality constant of dual problems. Agree? This now this I can write it second equation, that you see this coefficient is 1. So, 1 into y1 plus, that is minus sign, minus twice y2 plus twice y3 is greater than equal to what? Minus 2. So, I will write it y1 minus twice y2 plus twice y3 is greater than equal to minus 2. See this one. Agree? And we have a now new variables, a dual problem variables are y1 greater than equal to 0, y2 greater than equal to 0, y3 greater than equal to 0. Okay. So, as I mentioned is here, when you convert into dual problems, the right hand side of this constant does not have any restriction on its sign. So, we have converted into same this form. So, now if you see this one, then what is this? This is as converted into a that our standard dual problem. Now, if you want to solve this standard dual problem you have converted, then you want to solve it by using simplex method. That means, you have to convert, next is convert the dual problem into standard LP problem, and then solve by simplex method. Okay. So, first you convert into standard LP problems. This is minimization part is already there, we need not to, but this part is not in standard form. So, you have to make it in equality form. Now, see this one, when you will convert into standard LP form, right hand side must be sign must be positive. So, this one I can write it that you see this is greater than equal to this, that means minus some variable you have to make it it is equal to. I mentioned you that when it is this type of equation is there, if you just put a new variable y4 minus y4 is equal to 5, then you will see when you will solve this problem, the y4 value will not be restricted with a non-negative number, it may be negative number. To avoid that problem, we introduce what is called the artificial variables. So, these things I can immediately I can write it twice y1 plus y2 minus 3 y3 minus y4 plus y5, and this our y5 is your our artificial variable, and this is we called, if you remember, this is a surplus variable, slack variable, surplus variable, again artificial variable. This equation is converted into a. Now, this equation you can convert into a plus sign, because I have to make it plus sign and equality sign this. So, if you both side you multiply it by minus this equation, if you both side multiplied by minus, then it will be y1 minus y1 plus twice y2 minus y3, agree, then it will be less than equal to 2. That means, we have to add another artificial variable, let us call this is y6, agree, that y6 is equal to 2, and this is a slack variable. Now, tell me how will you solve this standard LP problem? Minimize this one subject to this two equality constraints, and out of this we have a this is an artificial variable, and this is the what is called surplus variable, this is the our slack variables. So, this we have to solve for y I is greater than equal to 0, for I is equal to 1 to 6. These are our problems. So, if you recollect this thing, if you have an artificial variable, we have to solve this problem in two stages. First stage, it will minimize the artificial variable, that is y5. If you have a more than this type of inequality is there in your equation, then it will come for each equation it will come one artificial variable, agree, and resultant cost function for the artificial variable cost function will be the sum of algebraic sum of all artificial variables will be the objective function. So, in this case only one artificial variable y5 I have to minimize, then y5 expression I can write it keeping all this variable in right hand side, then y5 is equal to I can write this expression. So, our phase 1, if you see our phase 1 problem is like this way, minimize w is equal to y5, and what is y5? If you see this one, 5 minus twice y minus twice y1 minus y1 plus 3 y2, if you take that side, plus y4. So, I am writing 5 minus twice y1 minus y2, okay, plus 3 y3 plus y4, okay. So, this is our objective function subject to what? This constraints, subject to y1 plus y2 minus 3 y3 minus y4 plus y5 is equal to 5, and minus y1 plus y2 to this two equation what we have written, same equation I am writing here, minus 2 y3 plus y6 is equal to 2. We have our original objective function is what? If you see our original objective function is minimize. If you see this one, minimize f d is equal to 9 y 1 again plus 2 y 2 plus 3 y 3. So, in phase 1 in tabular form we have to minimize first this one, then in phase 2 we have to minimize that one. So, when you will minimize in first one tabular form, both the function you have to write it simultaneously, agree. So, this you have to write simultaneously this one. So, I leave it as an exercise to work out, and you will get it after phase 1, after completion of phase 1, the solution of this one you will get it that after completion of phase 1 you will get the value of this, that phase 1, end of phase 1 you will get it the value of W is equal to 0, then 1. In phase 1 you have a 2 iteration that I am telling you. So, after the end of the phase 1 you will get W 1 is 0 means W is 0 means y 5 is equal to 6, agree, this 0, then you will get it y 1 value 2.5, y 2, y 3, y 4, y 5, these values are zeros, and y 6 values is 4.5. These are the basic variables you will get it, and these are non-basic variables. So, this is the end of phase 1. That means, we have minimized the artificial variable which we are expecting that y 5 value should be 0, it is coming 0. Then at the similarly next you ignore that y 5 in the tabular form, remove it from the tabular form this y 5, and then proceed for phase 2. If you see the phase 2, at the end of phase 2, in the phase 2 you are minimizing the objective function, the changed objective function during this process. When you did it phase 1, in this process the objective function is changed, because we have done a lot of elementary row operations there. So, it is changed it. So, phase 2, the end of phase 2, you will get basic variables y 1 star is equal to 1.6, y 2 star you will get 1.8, then y 3, y 4, y 5, then y 5, then y 6. No, that y 5 is not there, yes, y 3, y 4, then y 6, these values will be 0. Now, you see what is the objective function value, y 1 is 1.6, y 2 value is your that 1.6, y 3 value is 0. So, 9 point, if you see the f of d, this is 9 into 1.6 plus 2 into 1.8. If you do this one, this will be a 3.6, 14. So, it will be a, this will be a 18. So, f d value is will be at 18. Then what is our z value? Z value, how will you find out z value? We do not know the value of x. So, there must be some transformation from what is called dual variables to a primal variables, that we will discuss next class. But we can say this value, objective function value in the primal must be also same, agree, that 18. Okay, we will discuss next class in details how to convert the dual variables into a primal variables, design variables. I will stop it here.